My final project is improving neural value iteration. Hi, my name is Xiaolu. In class, we discussed the optimal control problem. The neural value iteration is an approach to this problem. We'll consider the goal of control as a long-term scalar cost function that we then want to optimize. For my project, I'm using the double integrator as my environment. We'll look at two cost functions, the minimum time cost and the quadratic regulator cost. So recall that the double integrator can be thought of as a block that is moving on a frictionless surface. So we want to find the optimal control that gets it to a final location that we desire. For the minimum time cost, we want to minimize the time it takes to reach that goal. For the quadratic regulator cost, we want to minimize the accumulated distance to that goal. So for the latter, even if the optimal time cost is moving back and forth just kind of wildly, that will not minimize the quadratic regulator loss. So minimizing one cost does not minimize the other. For my project, I'm looking at 4 different types of neural net architectures with 4 different types of activation functions: the sigmoid, tanh, ReLU, and leaky ReLU. So as a brief overview, the sigmoid and tanh function are known for the vanishing gradient problem, where earlier layers are not updated, like their weights are not updated as much as those of the later layers because of the vanishing gradients. The ReLU activation function solves this problem, but it has the problem of dying neurons because if the input is less than 0, if it's negative, then the output is simply just 0. So some of the neurons tend to die. And the leaky ReLU then solves this problem. But because our network is so simple and not very complicated, it's worth looking at all 4 types of activation functions. The results are shown here. We'll note that I'm using the mean squared error loss between the theoretical best cost and the predicted best cost, and so that's what's being plotted here. The blue line indicates the quadratic regulator loss, so that was the accumulated distance, and the red line indicates the minimum time loss. So these are the results for the sigmoid and tanh network across various learning rates. And then here are the results for the ReLU and leaky ReLU network. And so another thing that I did do is also play around with increasing the hidden layer sizes. And so that's not shown here, but using various activation functions as well as increasing the hidden layer size, I got as best results around 1.42 as the minimum time loss, the mean squared error minimum time loss, and I think somewhere in the 5,000s-ish for the quadratic regulator loss.